We will continue with the structure of solids. Until now we have looked at different crystal structures forming due to ionic, metallic and covalent bonds. Now we will go on to see how defects occur in the crystalline structure, and we will also look at non-crystalline materials which are called amorphous solids. So when we look at defects that occur in crystals, there are different types of defects, and these are classified as point, line, surface and volume defects. Point defects are where you have defects occurring in the particle level. These could be interstitial, that means that within the gaps in the crystal structure you can have a defect, meaning that there is either a vacancy or there is a foreign atom or a foreign particle in the structure. Substitutional is where one atom or particle is replaced by something else, and this gives rise to a substitutional point defect. These have influences on material properties. For example, the point defects can affect solid solution strengthening. Solid solutions are where you have alloys forming, mixture of different materials, and this could lead to strengthening because of the defects. Even though we call it a defect, it could have some beneficial effects like strengthening. Then we have swelling of clays that can also be attributed to defects, where you have some other ions being introduced into the clay. This could lead to the absorption of water and therefore swelling. Line defects are basically dislocations, where you have a discontinuity in the crystal array, and this has a lot of effect on ductility in metals and work hardening, because these are related to the movement of dislocations under stress. Surface defects are grain boundaries, where you have a discontinuity in the crystal lattice planes between one grain and the other, and this we discussed it to some extent in the previous lectures, where we saw how crystals nucleate and start growing, and when their growth interferes with the crystal that is growing next to it, then you have a grain boundary formed, and this again has influences on the material properties. We will see later how dislocations are impeded or slowed down by grain boundaries. So we find sometimes that when grain sizes are small, there is a strengthening because of the higher impedance to the dislocation movement. Finally, we have volume defects in crystals. Volume defects could be either pores, where there is an absence of material. This could give rise to stress concentrations, crack initiation at that point, and these defects propagating as cracks. We could also have inclusions, which can be considered as volume defects, and this also could increase the hardening effects called precipitation hardening in some materials. So as we said, point defects are certain points in the crystal lattice where an atom is missing, or an extra atom is present, or an atom of a different size replaces the expected atom. That is, the crystal structure is distorted at this point by something that is missing, an atom that is missing, a particle that is missing, or an extra or an additional atom or particle being introduced, or something of a different size that causes distortion of the crystal lattice at that point. Line defects are imperfections in the crystal lattice, where a line of atoms becomes mismatched or discontinuous, so there is a mismatch with the surroundings. Surface defects are grain boundaries. So there is an area of defect concentration. We will see that there is a large discontinuity in the crystal lattice at the grain boundary. So there is an area of defect concentration in the interface between the crystals or the grains. Lastly, we have volume defects, which are three dimensional. They are either absence of material, that is a void, or a foreign material, an extraneous material that is introduced in the material, which is an inclusion. So these are the different defects and we will look at them in detail. Starting with the point defects in the crystals, we see solid solutions as a mix of different metals. There is a base metal and then there is a different metal which is introduced and becomes a solid solution. Just like we have liquid solutions, a solid solution is a homogeneous mix of two different materials. And we can have two types of point defects: interstitial, that is what we have in the animation at the top, where we have this purple atoms or particles being in the interstices, that means the voids between the blue particles. So these are called interstitial defects in the solid solutions, where you have small atoms or small particles fitting into the space between the larger particles or atoms. That is what we see here. Then we have the substitutional type of defect, which you see in the bottom of the screen, where you have the blue atoms substituting some of the purple atoms. So here in the substitutional defects, we see that some atoms of the base material or the host material are replaced by atoms of similar size and chemistry. Now it has to be of a similar size and chemistry, otherwise they will not fit in very easily in the lattice. Sometimes you can have atoms of different size and chemistry and they have to be forced in, the lattice is distorted. We will look at that kind of effect in a minute. The point defects distort the lattice structure of the crystal, and this leads to additional strain being introduced in the lattice. This increases the energy of the crystal and the lattice binding energy is decreased. If you remember from the previous lectures, we said that always a stable structure is that which has the lowest energy, because when the lattice energy is lowest or the potential energy is lowest, you have the highest binding energy. But here what happens is, when we introduce a defect, there is a strain created due to the distortion. This strain increases the energy, that is, you move away from the lowest point in the Condon-Morse diagram, and this decreases the binding energy which is holding the lattice together. Therefore there is a limit to which point defects can occur in the crystal. Beyond this, beyond a certain stage, the crystal becomes unstable and cannot continue to exist. However, as long as point defects can occur, you can have some beneficial effect, like in the case of alloys. In alloys what happens is, we have a base material or a host metal in which different atoms of other materials, other metals are introduced, and you have a solid solution which eventually leads to strengthening or better properties of the alloy. This on this screen you see the example of copper being alloyed with beryllium, tin and zinc. On the right hand side you see a graph showing the yield strength on the y axis and the percentage of alloying element on the x axis. And if you see this case at the bottom, this is brass where copper is alloyed with zinc, and in the crystal lattice this is represented as the hollow spheres being those of copper, and then the solid sphere being that of zinc, and you find that zinc atom is slightly bigger than the copper atom. So there is some distortion of the lattice, not much distortion, and we find that as we increase the percentage of zinc in copper giving brass, you have the yield strength increasing. Now the question is, why does it increase? One way to visualize it is that when a material such as a metal yields, there is slip that is occurring in the crystal lattice, that is one plane in the crystal slides over the other plane, leading to shearing or yielding. Now when you have a local distortion like you have here, so you have a local distortion which is occurring here, you find that there is a bump created here. So as this plane and this plane slip over each other, there will be a bump, so there is a little bit of more force needed to create this movement compared to when this was not there. If this was not there, then both the planes will be smooth, so there will be easier slip occurring between the two planes. Now as this zinc atom is introduced, you have a distortion in the plane, so when slip has to occur, we can imagine that the slip planes now are bumpier or rougher, so more energy is required for the slip to occur. Now as the zinc atom is not very different in size and chemistry from the copper atom, you find that we can introduce up to about 20% of zinc in brass until the material can become unstable, and up to that we find that there is an increase in the yield strength from about 75 megapascal to say about 100 megapascal with about 20% of zinc. Now in the case of bronze, where you have tin being introduced, the tin atom is larger than the copper atom and also the zinc atom. So what happens here, when we substitute one of the copper atoms with the tin atom, there is a higher distortion of the lattice around. You can see that there is more distortion here, so this means more strain is introduced, and this has two consequences. One is that this imposes a lower limit on how much tin can be introduced in copper to give you bronze beyond a certain limit, of say here it looks like about 8%, the system becomes unstable. You cannot put in more tin atoms than about 8%. The other consequence is, now you see that the crystal plane is rougher, there is a bigger bump here. So when we have to introduce these slips or shearing over these planes, then you will need more energy to create a slip here, so therefore the yield strength goes up even higher. The yield strength is a consequence of the resistance to slip offered by the material planes or the slip planes, and what we find here is now this surface is now bumpier, and when this surface has to slip on this surface, you will need more energy to do so, and this drives up the yield strength to say about 160 170 megapascals. We can also have the case of smaller atoms replacing the copper atom. In this case we have beryllium, which is a very small atom compared to the copper atom. So when we remove one copper atom and we put in a beryllium atom, you see that there is a very big distortion of the lattice, there is lot of strain created, and the limit to which you can introduce beryllium in copper is very small, in the order of 1 or 2%. Beyond that the system becomes unstable because we have introduced a atom of a different size and chemistry. So this gives a graphical view of the limits of how much alloying we can do, how much extraneous or foreign atoms can be introduced in a lattice structure, and also the benefits of doing so, why the yield strength material alloy increases when compared to the host metal. We find that when we introduce an atom which is different from that of the host material, we find that there is a distortion of the crystal lattice, and this creates a mismatch in the atom size, and the crystal planes or the slip planes become rougher, and this leads to strengthening. Now point defects can occur in other materials like clays. Here you can have a point defect leading to a charge imbalance, where an ion of one charge substitutes an ion with a different charge. So, take the example of a smectite here at the top. So, this is a smectite made up of sheets of silica and aluminum hydroxide. This is the TOT structure that we had discussed earlier, tetrahedral, octahedral, tetrahedral structure, and these layers are bonded together by ionic bonds, and the clay is now made up of several sheets like this. Now, suppose we have aluminum substituting for a silicon atom. What happens is now there is a charge imbalance created. So, the smectite could become probably muscovite or montmorillonite, because now we have other cations which are introduced to satisfy the charge imbalance. This charge imbalance that has been created due to the substitution of the silicon by aluminum has to be compensated by other cations which get now introduced into the structure. There are cations which get introduced now in this structure, and this can lead to changes in how the material behaves. For example, when the silicon is substituted by aluminum, you can have potassium ions, potassium cations being introduced between the clay sheets. This gives us mica or muscovite, or you can have calcium cations being introduced between the sheets, and the difference between these two is now with the introduction of the calcium cation, the space between the sheets is now bigger. You can see here that is 1.5 nanometers, whereas when potassium cations are there it is only 1 nanometer. So, the space here between the two sheets now is bigger. This gives the possibility that water molecules can enter between the sheets, and when water molecules enter between these sheets lose some of their bonding and start separating, and this gives rise to the expanding behavior of some clays. So, as we said, the partial substitution of aluminum in the silicate sheets of the clay leaves the layer with a negative charge, since the aluminum 3 plus replaces silicon 4 plus. Therefore, external cations must now be located between the layers to balance the charge. So, there is a change in the charge because we have the aluminum cation replacing the silicon cation, and now you see that there is a loss of charge, and so external cations have to now come in between the layers to balance the charge, and these cations are of different sizes and charges. Size and charge of the cations now determines the distance between the layers, and this distance between the layers determines whether water can enter or not, and this changes the behavior of clays, and we saw earlier that some clays absorb water and expand, others do not. So, the reason why this happens are these defects which get introduced in the sheet structure and change the nature of their behavior. It is also interesting to note that point defects occur in pairs to avoid charge imbalances. For example, here we have two cations together, that is one cation is missing here and this is compensated by another cation here. You can have a case where there is a vacancy, there is one anion missing, and to compensate that in terms of charge there is also a cation missing here. So, we find that lot of times the point defects occur in pairs, so that there is less charge imbalance, or the charge imbalance is compensated by another point defect also occurring, and this also leads to minimum strain in the crystal lattice caused by the defects, that is the distortion created is reduced by the defects occurring in pairs. So, this is about the point defects. Now we said that the next set of defects are line defects. Line defects are where you have a line of atoms, instead of in the point defects we saw that only one point was changing. Here a line of atoms becomes mismatched, it is either missing or introduced. So these are called line defects. Line defects are known as dislocations. We will see how these occur and how these affect the behavior in a minute. Now there are two types of dislocations. First we will look at what is called the edge dislocation. An edge dislocation is an extra plane of atoms in the lattice. So we have a lattice here which has a regular array, but you will see that there is now these two atoms which have been introduced. There is a discontinuous plane, there is a set of atoms but it does not continue. This is as if it has been wedged into the crystal lattice. So if you can imagine how a wedge works, if you push this here, then you will have tension developing here and compression developing here. So that is what is shown here. So as this extra atom plane has formed, you find that there is compression here and tension here. So there is a distortion in the stress field whenever a dislocation occurs, and this we can see also in micrography. This is a crystallographic plane showing the dislocation aluminum. See here you have a plane of aluminum atoms inserted in this otherwise orderly crystal of aluminum. This obviously has been magnified millions of times, and you can see however this very clearly, this dislocation in aluminum. These dislocations move under slip. So when you have here say a crystal lattice with a dislocation here, and we are trying to shear or make this zone slip, this dislocation now moves towards an edge. So you see here in these diagrams, one by one the bond is broken and created. So in each step we have one bond lost and one bond created. This dislocation slips until it reaches an edge. This is called the slip plane. The dashed line is called the slip plane. This gives rise to yielding and shearing within a crystal, for example in a metal. Another type of dislocation is a screw dislocation, where you have a region that is distorted. Instead of a line being introduced, you see here that the plane has been shifted slightly, that there is this line which has moved up. You have here a line of atoms which has been moved up. So the screw dislocation is a region of distortion in the crystal lattice in the form of a spiral ramp of atoms. So you see here that it will spiral, like this plane has spiraled down, here it is higher and here it is lower. And the screw dislocation also moves under stress. That is what you see in the bottom diagrams. You see here a screw dislocation, and when stress is applied, again if we are trying to shear this material to try to make it yield, you will see that the screw dislocation moves until it completely covers an edge. Now we looked at how individual defects form and move, but in reality you will have lot of these dislocations occurring together and probably in a mixed manner. In this case you see here a screw dislocation at the edge, and here in the middle you see an edge dislocation. So now as the material is being sheared, both the screw dislocation and the edge dislocation move until they reach the edge of the material, until the structure inside is uniform. There is deformation, and this deformation becomes the slip that occurs in the material due to the stress. These are pictures again from the Manchester Material Science Centre site, showing images from electron microscopy showing dislocations in some materials. On the left you have nickel, and these lines that you see are the dislocations that occur and that you can see under magnification. Now this one on the right is aluminum, where again you see the lines, and these spots are all dislocations that are occurring in the surface, which can be seen in the through microscopy. A third type of defect is a plane defect. Until now we looked at what happens in a point defect, in a line defect. Now you have a surface which is acting as a defect. This occurs mainly in polycrystalline solids, where you have several grains or crystals forming the solid together. The interface between the grains, or the interface between the different crystals, which is called the grain boundary, represents an area of defect concentration, that there is a lot of defects occurring in a grain boundary. Defect meaning that the crystal plane becomes discontinuous, and you see that there is a gap between adjacent atoms in a grain boundary. There is no continuity. You can see in this diagram at the bottom that along the grain boundary between the white circles and the green circles, you see that there is no continuity of the crystal planes, there is a discontinuity. So this is called the grain boundary, and this is a defect, a large concentration of defects occurring in the grain boundary. When you see this diagram, you can imagine how each of these crystals or grains has a different orientation of atoms than its neighbor. So since each of these has crystal planes in different direction, when these crystals meet, when the grains meet, there is a mismatch and there is no continuity. So at those planes we find that the atomic spacing or the interatomic spacing will be larger than that corresponding to the minimum energy. So you have actually higher energy at the grain boundaries, and as you know, higher energy means that there is instability. We see that explained further here, what occurs at the grain boundaries. So here you have two grain boundaries, this is one and this is another, where you have the intersection between three different crystals. In this one you have the crystal planes running like this, in this one you have the crystal planes running like this, and here you have the crystal planes running like this. And when they meet, in this case there is some angle difference, a small angle is what is there between the planes of these two crystals. So you find that the distances between the atoms at this grain boundary are more than inside the lattice, but not too much. But if you see here at the top, you see a bigger misalignment or mismatch. This plane is going this way, but now the adjacent plane has a bigger angle, much more than 180 degrees here. You see that there is a big angle here, and therefore you find that along this grain boundary there are more gaps between the atoms, and there is a lot of discontinuity here. So this increases the energy at the grain boundary. Instead of being at the minimum, you are at a higher level of energy, and as we said, always a material will look to minimize the energy, decrease the energy, and when the energy is higher it is unstable. And this is the reason why you have diffusion occurring along the grain boundaries, and you have chemical reactions occurring first along the grain boundaries. So as we said, and grain boundary, there is a mismatch which depends on the angles of the crystal planes of adjacent crystals. There is therefore a grain boundary energy or an interface energy which is now created, and due to this interface energy, the atoms at the grain boundary are chemically more active, because they are not at the minimum potential energy or the minimum lattice energy, and to decrease the energy they react with atoms coming from outside the element. We also find that whenever the impurity atoms get into the material, they also concentrate on the interfaces. When you look at a metal which is corroding, you generally will notice that corrosion starts at the grain boundaries, because the grain boundaries are at a higher energy level, they react more easily. So corrosion starts a lot in the grain boundaries. Later on when we look at stress corrosion, you will see that stress corrosion cracking develops also along the grain boundaries. Another type of defect is a twin boundary, where you have a distortion of the crystal plane again occurring, which is called a mirror lattice symmetry. There is a symmetry here, but there is again an angle of more than 180 degrees between the adjacent crystal planes. This is called a twin. Now the twin can occur because of application of shear forces or heat. Imagine that you have a crystal structure like this, where you are shearing, you are applying shear force, and you can possibly create a distortion here like the twin. So you see the symmetry here, this is the plane around which you see the symmetry, this is symmetric to this is symmetric to this, and so on. So this is called twinning, which can also be considered as a defect along this boundary between the two parts of the lattice. Now this type of movement requires more energy than just slipping. At the top here now you have a slip plane, say you have a dislocation moving and a slip occurring along this plane, and you see here when this slip is occurring, at each step only one bond is broken and a new bond is created. But when you have twinning, you see that many bonds have to be changed, so that the whole crystal lattice can get distorted like in the bottom diagram. This is called the twinning plane, and this requires now higher stress to produce this than just slipping, which you see in the top. The last type of defects is a three-dimensional region of defects called volume defects, and they can be of two types. They can be voids, which means that there is an absence of material, or they could be an inclusion where there is another phase or another type of atom being introduced in a large volume, and these are usually considered to be outside or external to the crystal structure. You have a crystal structure and there is a gap in the crystal structure that is outside the crystal structure, or there is a volume that is introduced again outside the crystal structure. There is no continuity of the crystal structure through the volume defect, be it a void or inclusion. So as I said, voids are pores or incomplete filling of available space. Inclusions are regions of a second phase, some other material being introduced within the single grain. Here you see a picture of grey cast iron. Cast iron is an alloy of iron with 4% carbon by weight. On the left you see an electron micrograph from the Manchester Material Science Centre, where you see that the microstructure has two constituents. The background or the matrix is the alloy called pearlite. This is this part. Pearlite is a mixture of ferrite, which is the phase of iron, and iron carbide, which gives that wormy or the striped structure. Other than that, you see these long pale flakes, this is graphite, which is precipitated due to an excess of carbon in the alloy, and this forms flakes inside the grey cast iron. Now this is an inclusion within the rest of the structure. The graphite is now an inclusion. So what happens when this material is subjected to stress? we find that the cracks develop along the graphite, because the graphite is weak. We have seen how graphite behaves, it can slip very easily, it does not offer a lot of resistance. So cracks propagate very easily through the graphite. So that is why cast iron is brittle, it breaks very easily because cracks can propagate through it, even though the rest of the material is ductile. Here we see mild steel with another type of inclusions. The structure itself is made out of two major constituents, ferrite and pearlite. The alloy is made out of ferrite, which is the light colored space, the light colored crystals are ferrite, and the striped regions are pearlite. This is pearlite. So this is pearlite and this is ferrite. So this forms the bulk of the material. However, you have small inclusions here, these spots here. These spots here are impurities which are now included outside of the individual crystal lattices, which could be oxides or sulfides. So this is also another type of volume defect introduced in the material. So we have seen now different types of crystals, crystalline structures, and how defects occur in the crystalline structure. Now we will move on to materials which are not at all crystalline, they do not have any orderly structure, and they are called glasses or amorphous materials. And to compare, you have two structures on the screen. On the right is crystalline silica, you see an orderly structure, you have an ordered structure here, and which you can see better here. The same silica can occur as a glass, very disorderly structure, you do not see any order at all, no particular arrangement, and this is now a non-crystalline or amorphous structure. So we call whatever has an orderly structure as a crystalline material, and which has a completely disordered structure as an amorphous or glassy material. Glasses or amorphous materials form, for example, from melts when the rate of cooling is very fast. We saw before when we talked about crystals, there are different stages of growth in the crystal. From a melt, first you have nucleation, and around these nuclei slowly these crystals start forming, then one crystal meets the another and a grain boundary is formed. Now for this to occur, a certain amount of time is required, the rate of cooling has to be slow enough so the nuclei can form and the nuclei can grow into orderly crystals. Suppose we do not allow the material to cool slowly, we cool the material very fast, then there is no time for this ordering of the structure to occur, and you have a glass forming. Okay? So that is what is said here, when the rate of cooling is too fast to allow nucleation and the growth of ordered crystals, a glass is formed, an amorphous structure is formed. Because for a crystal to grow, that is an orderly structure to form, enough atoms must come together in the right packing to create the minimum energy, only then a crystal is formed in a stable way. Until this happens, the energy will have to be used to overcome repulsion, the atoms try to separate, and until you have enough energy they will not come together. So this results in a nucleation barrier that has to be overcome when crystal growth can occur. Thermal energy or heat can help atoms overcome the nuclear energy, you need a certain amount of heat for the nucleation to occur, and that is shown schematically here, where we see the potential energy, how it is changing as the state is changing. This is the potential energy, and we go from a molten state to a solid state passing through a nucleation state. So for this you need some amount of energy to be surpassed, you have the nuclei forming, and if the cooling is too fast you get a glassy state, you do not go to a crystalline orderly state. Only if from the molten state to the cooling, you allow for enough time, you can reach the crystalline state, and this can be thought of in terms of thermal energy also. Thermal energy E sub T only when it is large enough compared to the nucleation energy, which has to be overcome, you can have spontaneous nucleation occurring leading to crystal forming. If the thermal energy is in the same order as the nucleation energy, you can have the system go one way or the other. Nucleation occurs when the cooling is slow, and glass formation or amorphous structure formation occurs when the cooling is very fast. If the thermal energy is much less than the nucleation energy, only a glass will form. Okay. So basically what we have to remember is that there is necessity of a certain thermal energy to have nucleation which is required for crystal formation, and if the cooling is very fast, there is a higher tendency for a glass to be formed and amorphous structure to be formed. Now amorphous structures like glasses also, even though when they have random packing, can be considered as ideal defect free structures, like in the case of fused silica. There is a random arrangement of silica tetrahedra, but they need not necessarily be defects in the structure. On the other hand, in soda glass we have the sodium cations replacing some of the silicon atoms. The arrangement is disrupted by the sodium ions, and instead of the silicon oxygen silicon bond, we have a silicon oxygen sodium bond like you see here. So here there is a distortion, here there is another distortion because of this defect caused by the sodium cation replacing the silicon. Due to this distortion, what we find is soda glass when compared to fused silica has a lower binding energy and therefore melts at a lower temperature. Remember when we talked about ionic materials, we said that higher the binding energy, higher will be the melting point. Here what we find is glass changes when the silicon is replaced by the sodium, you have a distorted structure, you have a lower binding energy, and therefore you have a lower melting point. Now we have covered different types of defects, we have also looked at the amorphous structure of some materials, and in the next lecture we will continue to look at more of amorphous materials. We will talk also about polymers. Polymers can be partially crystalline and partially amorphous, and we look at what are the specific characteristics of polymer materials and polymer chains, and see how this gives rise to the elasticity, the viscosity of polymers. Thank you.